to have Ibrahima from Johns Hopkins tell us about topological operators in quantum field theory and their fate in gravity.
Thank you for the introduction. Okay, so first I should say thank you on behalf of the Islamic collaboration for allowing us to use your space. I know this could be quite an event to see this whole space filled. So we appreciate it a lot. And part of that, I was asked to at least tell you guys what our collaboration is about and what are some of the questions that we care about. So to this light, this talk is going to be broad, probably more broad than you might used to see. But if you want more detail, please ask, I'll be happy to provide. And also, because I'll try to give an overview, I'll be very light on citations and such. But so don't get offended if it seems I'm taking credit for all. So the talk will split into, it'll be two parts. The first part, I'll try to at least tell you what the collaboration is about, which is the study of topological operators in quantum field theory, why that is an interesting problem, and why does it require both mathematicians and physicists to work together to try to understand these questions. And then the second part, I will tell you about some of my own work, which should hopefully appear tomorrow. It was supposed to be tonight. Tonight will appear tonight, but it's again related to studying topological operators. Does it tell you anything about gravity, which is a question that I care about and many people here care about also. So please interrupt me for any questions, and I'll be very much enjoy having a discussion. Well, to that end, I've given a few talks here. The first ones that I've given, I had slides, and then questions started, and I gave an entirely different talk on the board. So there's a precedence for it. Okay, so let's move on. Okay. Okay. So the big picture of what happened is that global symmetries, we love them for various reasons in the study of quantum systems. But recently, there's been a huge sort of revival in the study of global symmetry as a thing. And this picture came from the fact that the idea of a global symmetry is synonymous to having topological operators in quantum field theory. Okay? So that sort of removes the idea of thinking about charges in groups to thinking about a class of operators that should exist in quantum field theory and what do they do. So the sort of intuition why these two global symmetries should be related to topological operators in quantum mechanics, if we think about a symmetry operator is the object that commutes with the Hamiltonian for a unitary symmetry operator. And then such a thing is preserved under any deformation, so the Hamiltonian produces a thing. So in quantum field theory, a related version of that, an object that commutes with the stress tensor is what we would call a symmetry that's acting. And we think of both the Hamiltonian and the stress tensor as generating small deformations in space-time. Okay? So then from that picture, something that commutes with an action of small deformation is going to be topological in a sense that which mathematicians might care about. So that is the sort of intuition why topological is related to having a global symmetry. So so having this idea, now we should think about these guys, but of course this should be interesting because symmetry already we know, they give us constants of motion which are preserved in the RG flow and time evolution. There are all sorts of nice effects. Superselection sectors, they control EFTs, RG. They're the full Landau paradigm that we know and love and typically study. So to put more specifically, let me briefly reformulate things that you've already seen and know in this context. So what we usually call ordinary symmetries that we study from grade school is codimension 1 topological operators, meaning in 4 dimensions, if I have an operator which has some charge and I want to measure the charge, I surround it by a 3-dimensional surface in 4 dimensions, and then shrink that, it gives me the charge. So in this example here, I have some operator, I want to measure the charge. There is this extended thing, which when I shrink it, and it crosses O, it gives me a phase, which is what I would typically call the charge in the case of a U1 symmetry. And then if I have two of these operators, I can stack them. And then when I stack them, this is the idea of multiplying two symmetry operators. And then the labels are related to the group that we associate. So this is things that we're familiar with. So why is this topological? It's topological in the following sense. So we define the operator as exponentiating the charge, okay? And the charge is given by an integral of a current on this three-dimensional surface, okay? The thing that is true is because the current is conserved, so d of star j is 0, if I take this surface sigma 3 and I deform it a little bit, right? And then I can use Stokes' theorem and compute the difference of the charge associated to this surface versus that surface. And because of the conservation law, this is 0, right? And this is exactly the statement that if I give you the surface, right? So the symmetry U depends on the surface, right? So the symmetry is a function of the surface given the label alpha, and it depends on the surface in a topological way. Small deformation of the surface is not going to change the value of this operator or its value in correlation function, which is the critical fact. Something interesting happens only when, let's say that this deformation, there is some charge sitting here, then if I try to push past the charge, then I would get some delta function here, which then this would just measure the charge, and this would relate to that. So nothing interesting happens for a topological operator unless they cross some charge object under it. Okay? And another way to more abstractly say this, inserting the symmetry operator is measuring the representation by which the charge is hidden. So the story doesn't end there, okay? So in addition to having, so we used to, of course, thinking about local operators and having charges associated with them, but you can also have extended operators in quantum field theory, which carry some constants, some parameters associated with them. The examples, for example, Wilson lines or surface operators exist in quantum field theory, and there must be something that can measure the charge associated with that. So this leads to an idea that there is the currents, which are called higher form currents, whose charged objects are extended themselves. So it would be, instead of having a one form current, you can have a higher form current, and you have some conservation law here. And if I take such a current, I would integrate it on a surface with a higher codimension.
So you're always in the Euclidean domain. Right?
Yes, it is important that we're working in the Euclidean domain to make sense of this. There's a lot of important questions you can ask. Please ask them later on that. Okay. So for the sake of this talk, let's say that. So in these examples here, right, you can have an extended operator like a line. You can measure the charge associated to a line, but it cannot be a three-dimensional surface, right? It has to be something lower that just links to it non-trivially. So the object that links to it here is in general, if I have a p-dimensional charge object, the thing that links to it has dimension d minus p minus 1, which measures the charge. Okay. So in addition to just having the codimension 1 topological operators, you also have a whole tower of topological operators of any codimension going from 0 to d minus 1. So already that's an interesting generalization when you move from thinking about the standard group picture to thinking about topological operators. So topological operators exist of various dimensions. And then from this perspective of a topological operator, there's no reason to actually tell you that if I take two operators and I put them on top of each other by multiplication, that I would get a unique operator on the other side which fits. Generically, what you expect to get, if I take two operators and I multiply them, I get some linear combination of other operators here. Okay? So this sort of statement here, of course, tells you that there is something special about what my linear combination means. And without going into details, is that I'm forced to think about such a linear combination if I want to preserve locality of quantum field theory. if you want more details, I can tell you more details why that is true. But in general, if I have topological operators and I take the product of any two, so we think of this product as fusion, then I should get some sum, not a unique thing. So what this means, this has a rather interesting implication, which is that because of this fact, if I have an operator and I take its Hermitian conjugate, where Hermitian conjugate here is defined as orientation reversal, right? There is no reason generically, if I stack them, I don't get an identity operator, which you might expect for a group. Okay, generically, what you get when you do such a thing, you will get one plus something else.
This wiggly sign refers to expansion in what?
This wiggly sign is the isomorphism. It's actually stronger than equal. It's weaker than equal. There's isomorphism choices, which is not important here. But from a physics point of view, it's equal.
Is it always involving the identity operator?
Involving what?
The identity operator.
So good. So when I take an operator and its inverse, the leading term is identity plus other things. Yes, the identity is that. Simple. Any questions?
And the composition is associative.
Yes. Yes. Okay. At least for this talk, we will assume. Okay, wait. Good. So this picture of having symmetry operators that are non-invertible is actually not super new in physics. For d less than 3 in 2D and 3D, there are many examples of this known. Yifeng is an expert, probably the world expert on such a thing here, where there, we have like modular invariance and other things. It really tells you that operators that I have to consider, can have this non-invertible fusion, and that leads to many other interesting results. The simplest example that comes from this is what we call the Ising fusion category, which is that if you take an Ising system in 2D, there are spins. So there is a Z2 symmetry corresponding to which acts on local spins. And then there is also a duality, which is Kramer-Wanier duality, which typically exchanges an ordered and disordered phase. So at the fixed point of such a duality, there's a sigma, which is an operator that maps between the ordered and disordered. So this has a fixed point, which is a conformally invariant point. So at that fixed point, the duality operator acts like a symmetry, right? Because it maps the theory to itself. So, and then if you look at that example, if you take sigma squared, instead of being the identity, is 1 plus eta, which is the Ising spin flip that we have. So that's one example that's been known for a while, yes.
You wrote the last triple them please, or was the simplest example in the Eagle trade?
So I cheated a bit. I think the Ising fusion I can also talk about in 3D.
You're thinking about topological field theories?
Yeah, I'm thinking about topological field theories in general. So we have examples of topological field theories that we study all the time. Or, if I have any 2D that I extend to the bulk, have some non-trivial EQFT, which has some interesting higher fusion rule. Okay. Thank you for the question. Okay, so what's new from more recently that led to many exciting things is that, this sort of funny symmetry action is not just restricted to 2D and 3D. It's actually very interesting in higher dimensions. And recently, we figured out a way to basically construct examples in higher D in very simple theories that we know and love. And that sort of led to the excitement of all of this. One of the simple examples here due to Shuhang, Hotat, and is we think about a U1 gauge theory with a U1 global symmetry, which have an ABJ anomaly. Okay, so the ABJ anomaly we just tells us that if you have a current which has an ABJ anomaly, it's not conserved. Okay. But even if you go back to the paper, to the original paper, you can in principle consider define a new current, which is J, shifted with this A wedge dA, where A is the bulk gauge field. So if you look at this guy is closed, and it does define for you a topological operator. However, although it gives you a topological operator, it's an operator that's not gauge invariant. It's not invariant in the large gauge transformation, and this is why people thought it might be troublesome to have such a thing. Okay. However, the thing that the cool idea that you note is that instead of thinking about this in this way, you should think about the fact that you have this constraint. What is it telling you is that when I have this star J operator inserted, there is that insertion is not gauge invariant, right? This is what this tells you. But what you can do is you can show that such a term you could recover by adding what condensed matter people call statistical gauge fields, which is going to be some level n Chern-Simons theory, which couples to this bulk field in this way, okay? So this action now is invariant under the bulk gauge transformation. And the picture that you have is that there is a inflow of a bulk current, of a bulk current onto this surface, and then you need to absorb it in some way. So the operator has to have a coupling to absorb this inflow of a current so that you can preserve the conservation law.
The condition for this to be rational is for not having some singularities.
Come again?
The condition for this alpha to be rational.
The condition for alpha to be rational is related to exactly this inflow picture that I've just described. It's not an issue of singularity. It's just an issue that which part of the gauge symmetry do I get to preserve when I do this trick.
So what happens when it's an irrational number?
It's not going to be gauge invariant.
There were some proposals, right?
There is some proposal, but that proposal is that you add like some sort of axion, some Stickelberg field on the defect instead. I mean that is there, and that could be realized in some sort of stringy model, but that actually there are some properties of how this symmetry should work, which such a proposal doesn't quite realize. That's why.
So this operator UA is not gauge invariant if sigma has a non-trivial pi1. So not just for if it's
yeah, it's not gauge invariant in the large gauge transformation. In the local gauge transformation, it is if sigma is closed, and the large gauge transformation is not. Okay, and that's precisely the point, right? So, however, if I consider this operator, right? So this operator still gives me the same property of this current, but now this is operator is gauge invariant. It's actually, instead of a U1, is Q mod Z. It's valued in the rational numbers. But the price that you pay by defining this operator, which is now gauge invariant and well defined, is that if I take U and I multiply it with its Hermitian conjugate, I don't get one. I get a sum of operators, which is exponential of integral of f. So this is an operator that measures magnetic field lines, that counts magnetic field lines in the conservation of magnetic field lines. Okay? So this is exactly the sort of trade-off you can construct. You see that you actually, because of the ABJ anomaly, you haven't lost the U1. You have a Q mod V symmetry that's acting on the quantum field theory, but it is non-invertible. Okay? It has, if I take the operator with its Hermitian conjugate, I don't get an identity. I get a sum of operators of higher codimension that acts on my physical system. And in fact, the only thing that sees this non-invertible structure in this quantum field theory is things that have like monopoles and such. Go ahead.
I was just the choice for this statistical gauge theory. It's not unique, or it's unique.
Good. So we can talk about the uniqueness there. So So good. So here, this choice of a statistical is like the simplest thing that if you were to just close your eyes and just evaluate this path integral as a continuous field, that means that you integrate out this A field, and then it will give you something that looks like that. right? But of course, that's illegal when you're doing that sum by just treating it as a continuous field. We can talk about that. Your question is, to rephrase your question is the following. When I do this trick, what I'm doing is I'm taking the, this will come up later, I'm taking the operator, right? And then I'm stacking another theory that lives on it. And the constraint of that theory is that it has to have the right anomaly to cancel this anomaly inflow, okay? From this point of view, this is not unique. Any theory that you put in there that has the right anomaly that can cancel it is a good candidate to make this. But the difference is that this is the minimal thing where you have where all the operators of this Chern-Simon theory actually talk to the bulk. Okay, all the extended operators of the Chern-Simon theory, in this case, they talk to the bulk. You can tensor in any bunch of stuff on the operator that don't talk to the bulk. And that is the difference in the question of the uniqueness.
Will that extra stuff affect this C gamma, or that only depends on the
It doesn't.
invariant?
It doesn't. It doesn't, right? It doesn't. And I will say a little bit, I can say a little bit more about this question. Okay. So recently, of course, starting with these sets of papers, we started to have examples of how to construct this in standard, simple quantum field theory. So then this is worth a study and try to understand what to do with it. Okay, so this sort of introduction leads us to the point of the collaboration that we call categorical symmetry. So as we just noted, right, what we basically are observing is if you have a quantum field theory and have topological operators in the quantum field theory, what that means is that there are operators that on their world volume lives a topological field theory, okay? And this topological field theory can couple non-trivially to the bulk. And because it couples non-trivially to the bulk, it should lead to some conservation law. So a heuristic picture of this is, for example, if we take this operator here, right, we can see how this works. So there is, in the action, there is a leading term, which is just star J, right? This is a part which was measuring the original current in my system. There is a Chern-Simons theory, which is a DQFT that lives on the operator, that is inherently defined that lives on the operator. And then there is a term that couples the Chern-Simons term to the bulk, okay? So this is an example of a DQFT in the quantum field theory that is coupled non-trivially to the bulk theory. And such operators are going to be what we call the spectrum of topological operators in the quantum field theory. And they can exist, so here is an example where it's a 3D operator, but you can have higher codimension ones, you can have surfaces, you can have lines, you can have points, and for each one of these you can have a non-trivial topological field theory that lives on it, and that non-trivial topological field theory can couple to the bulk. Okay? And when it couples to the bulk, then it should constrain the bulk via some selection rules and such. And even more fun, right, is that these operators themselves, they can act on each other, right? In addition to having this general non-invertible fusion rule that we talked about, which is beyond group-like, they can also act on each other. And you can have even operators where other operators live on top of them, which are of higher dimensions, okay? So the picture that you're now getting is that if I think about a quantum field theory, there is this crazy sector of extended operators which, talk to each other in some various ways. And all of those extended operators, they commute with the Hamiltonian of my system. Therefore, they should give you all the nice things we expect symmetries to do, okay? And in fact, I would call this as being from a quantum field theory point of view, the kinematic sector of quantum systems is going to be this sort of rather complicated beast. And then from a mathematical point of view, you can ask what sort of a structure describes or characterizes you have this whole tower of topological operators from 0 dimensions all the way to d-1. They talk to each other, they do all sorts of funny things. For example, the term higher group that you've heard about is related to having at each level, where these are symmetry operators that look like groups, but then they act on each other in a non-trivial way, so they give you this idea of a higher group structure, which some of you might have heard of. So this whole thing, this whole edifice, is what we would like to call fits into the framework of what is often called high fusion categories. So a category is a specific set of mathematical things. I will not go to define it. And fusion here is that the object in the category basically can talk to each other in some particular way to lead to some other thing. So from a physics point of view, the kinematic effect of quantum systems is going to be somehow described by a higher fusion category. So now, what is a math problem? The math problem first is, how do I define a higher fusion category in a way that I can actually play with it and control with it? And this is why this is interesting. It wasn't actually, the paper that classified fusion 2 categories, which is a relevant thing for 3 dimensions, 2 plus 1 spacetimes, just came out yesterday. It was yesterday in the archive. What is a higher fusion category? This is something for which there is no agreed upon definition in the math world, let alone know how to play with it, right? So this is from this point of view, we're seeing that this discussion of this physical system is leading to the development of, is pushing the mathematician to understand what this structure is, because now it is very interesting. And then, of course, from this perspective is, if you have if you have a good solid pitch of high fusion category, right? So this is supposed to replace what we call groups in quantum systems. Then you want to know what are their representations. This is a math problem, and there are many exciting both math results and physics results there to be obtained. And how do you characterize the state space that emerge from such a representation here?
The fusion category replaces a finite group, right?
I'll come to this.
Okay.
Good, very good. That's you're predicting the next big bullet point, right?
Okay.
Which is the fact that even in what is understood for this higher fusion category is only for finite symmetry, right? Which is the point that's just made. Okay. For continuous symmetries, which is the thing, which is the bread and butter of us physicists, because we know how to do continuous things. Actually, there is no idea how to even start and to describe this in a concrete way. And there's a question? Okay. So all of this in the math world is related to understanding topological field theories, because these higher fusion categories are related to some topological field theories. The higher fusion categories are, in many cases, you can think of them as being synonymous to the study of topological field theories in higher dimensions. How do you classify them? And and also another thing related, having a sort of a rigorous understanding what topological field theories are, and this seems to be a very strong hint of what you should understand, in math, is going to set the stage to start to actually think about how to rigorously define the quantum field theory, which is a very important problem for mathematicians also. Question? Okay, so what is a physics problem? So the physics problem here, again, how do physical systems manifest this structure, right? The structure has already been there. How do we manifest it, and how do we see it? So physical systems, of course, we know in condensed matter, there are TQFTs that appear, which are very interesting in characterizing topological phases of matter. Such a TQFT will encode such a categorical symmetry. And for some of us who are string theorists and holographers and so on, examples of these categorical structures naturally emerge from the string theory, and I'll say a little bit more about that. And then the questions, again, we would like to understand as a physicist is, what are the representations and how do we characterize the state space? And of course, the big thing that's been quite important in having symmetry in physics is that symmetry allows us to classify phases of matter and IR dynamics, okay? So this is generally put as the Landau paradigm. But then if you have all of this higher symmetry structure, you would like to understand what is the Landau paradigm, is categorical symmetry, what sort of phases that is classified. And then you can ask questions about anomalies, because if you have anomalies of these things, they should constrain RG flows and effective field theory that you might construct. So these are physics questions. And you know, I can list this set of questions. And one of the sort of interesting that appears is the classification of topological phases. So in quantum field theory, for example, we used to think about Higgs, confined, and Coulomb phases. Because of these non-trivial TQFTs, you can have new phases that do not fit into any of these paradigms. Okay? And then what should that look like? How should I think about them? Are there order parameters associated with them? And what is the physics of those order parameters? Okay? So all of these questions are quite exciting, and all of these questions basically are the raison d'etre for our collaboration. Okay? Any questions? Okay, so from a stringy point of view, right? We used to thinking about obtaining field theories by starting with a string theory, either decoupling gravity in some particular way, or through the ADS-CFT correspondence in holography. Right? We used to study quantum field theories in this way from a string theory. So you could ask, if you have this higher structure of categorical nonsense, does this actually come from anywhere interesting, and do you actually see it? So it turns out from various works in recent times is that if you take, you know, string theory is a theory of gravity, you have many dynamical extended things, brains of various kinds that sit here. When you go through these limits to get to the field theory, you often find that these systems, they're non-topological degrees of freedom freeze or decouple, and they yield this rather amazing edifice of these higher fusion, these higher categorical structures, right? So within string theory, we have reasonable evidence to see that actually when you do what you're supposed to do by decoupling gravity, a lot of extended dynamical things become topological operators, and they give you this structure. Okay. So this has been sort of exciting. For example, right, for the string theorists in the room, you know, one thing that we know is that we have things like tachyon condensations of D-branes. If you look at tachyon condensation of D-branes, where you take a D-brane and its conjugate and you multiply them, you get some lower branes that emerge of various kinds, depending on the bundle structure that you have in the brain. So such a process actually, through this decoupling of the non-topological degrees of freedom, exactly realizes this sort of non-invertible fusion that we saw earlier. So string theory has been one place actually where we can study this. Okay. But now this raises another question, which I will go to the next slide, which is that string theory is a theory of gravity, and in gravity, we know that we expect that there shouldn't be any charged quantities, symmetry is violated in all ways, and this is a very, very old thing that goes all the way back to Hawking, actually even earlier to Wheeler, where we expect there to be no symmetry in gravity. So what does this mean for this new paradigm? So there's no global symmetry in gravity for this new paradigm. What it tells you is that there's no topological operators in a series of gravity. And more particularly, no categorical symmetries in theory of gravity, okay? So this raises a rather interesting question, which is that if I take a quantum field theory and I couple it to gravity, what happens to all of this structure that we believe is there and it exists? Already, you kind of got a hint from it here, which is that there are things that live here that give me this structure. Is there a meaningful way to go backwards? Okay. Is there a meaningful way to go backward? Do you learn anything more sharp? Okay, so this is the next question. So I'll pivot now to something a little bit more specific. Any questions? Okay. So to try to think about this problem, we think about topological operators slightly differently in a paper that we should have soon, which is that instead of, so we typically we'd say a topological operator, we exponentiate the current and then we just insert it in a path integral. There's another way to think about it, which is that what is this supposed to do? When you insert an operator in field theory, what is it supposed to do? What it's supposed to do is that if you have fields in your system, across the operator, the field transform to whatever value you want them to transform to, right? So if this is a U1 symmetry operator, the field would have some U1 transformation that occurs. So from this point of view, roughly you have, the insertion of an operator tells you that your fields are basically have some step function jump where I'm identifying phi here with phi prime, where phi prime is the rotated guy and there's a symmetry transformation. So quantum field theory, of course, does not like singular insertions, right? Whenever we have singular insertions in quantum field theory, we have to regulate it in some way. And in case of currents, where it's an exponential of something, and I have, when I expand it, I have products of many things, which have many contact terms, which is a singular thing in quantum field theory that requires regulating. So one way you can regulate such an insertion is that since you know that what the operator is actually doing is saying that across the operator the field is transformed by whatever symmetry that I want to care about, is instead let me add a width to this operator. And instead what I will say is that I have a field profile where very far away, where at distances much larger than lambda, I have phi, and then very far away in the other direction, I have the symmetry transformed guy, the rotated guy. So what this does is that it takes this singular thing and it gives it a width and it regulates it in some particular way. Okay? So this perspective basically is saying that in a quantum field theory, if you actually want to play with this thing in correlation function, we should treat it more like a soliton with some width, and then we have to say something about when we take the zero width of it. So the profile that you pick that gives you this width for this thing regulates the insertion in a very specific way. And the thing that must be true is that when you take lambda to zero, right, when you take this width to zero, this basically should give you all the things that we expect when we do symmetry transformation, right? Because it's a regulator for my system. So, okay, okay, that's step one. So step two, as soon as you decide you're going to think about a topological operator insertion as being a field profile where you have some asymptotic boundary condition, and you're treating it as a soliton, such a process is a field configuration that spontaneously breaks the translation symmetry. And when it does that, you should get Goldstone modes associated to that direction. So that's one way to think of this. Another thing to also observe is that because of this spontaneous breaking where you have this Goldstone mode, another way to think about this Goldstone mode is that when you do an insertion, you also have wiggles on top that can live with it, right? So typically those wiggles we don't think about, but these wiggles you should see as a Goldstone mode. So when you do this regulating procedure, in addition to tell me that at lambda goes to zero, everything is fine, you also have to demonstrate that this Goldstone in fact decouples so that you get a well-defined topological operator that doesn't depend on its shape. So the regulator here also allows us to study what happens to Goldstone modes associated to topological operators. Okay, and in particular, what we should find is that in the zero width limit, the Goldstone mode should decouple so that I have a well-defined operator that only depends on its topology, not on its shape. So let's do a simple example to see what we mean. The simplest example that we can write is the shift symmetry, right? We have just a free scalar which has a shift symmetry. And in this shift symmetry, we're saying that we inserted some operator associated to this U1. What it means that the profile that we pick, phi, is alpha plus f of lambda, where f of lambda has a limit of a theta function, right? So that means that over here I have the field phi, and over here I have phi plus alpha corresponding to the symmetry transformation. So if I consider now this solitonic object as to study, I can plug it into the action and try to see what it does. Okay, when I expand this, I get the original kinetic term, then I get two new terms. So let's try to understand what those are. So the first term here is that because in the lambda going to zero limit, f goes to a theta function, its derivative goes to a delta function. So the first term here just recovers another current associated to the shift symmetry. Okay, so you can see that this picture of treating the topological operator by the field profile does indeed insert the current in the way that I expected to insert it in the fast integral. There is a term here that appears, which is the dynamics of the collective coordinates, or the dynamics of the ghost tone, which is appearing in my system. And then, universally, you will get some operator, here is 1, which basically you can remove by some counter term. This is like the energy of the defect. So,
this T of x is fixed, though. This T of x is fixed. This is your location of the defect.
There is T at T naught, and then the fluctuation above. So T of x is the fluctuations.
What's like, so
So it's a lower dimensional field. Because
yeah,
it
and
depends
so
on the
normally
coordinate.
when you talk about the defect, you said that the location is fixed. Now you want to make it dynamical.
So the location is fixed. I'm studying the fluctuation about the position. That's what I'm doing. And let me finish this line of thinking, and then we'll right. Good. So this is the point. So I gave the defect a width. I expanded it a little bit. So to go to the thin defect limit, I take lambda to 0, right? But then when I do this in this solitonic picture, I have this ghost tone that can wiggle.
You want to think of the defect as low energy limit of a real dynamical excitation.
Yes.
Not of a
Yes. So good. So from this perspective here, you can ask what happens to lambda going to 0. Here is a place where you can actually see that this mode actually just freeze, right? When I take the lambda to 0 limit, I have the kinetic term here. The only way to kill this operator is if this mode freezes. So the dynamics of this freezes, and then you recover, and the only thing that is left is a term which is you can remove by a counter term, and then you're just left with the current, which is the insertion of the symmetry operator. Okay. So this is the point that you have to make, that if you pick this regulator, then you have all of this data that you need to think about more carefully. Okay, good. So now comes the big question. What happens in this definition of the operator when you turn on gravity? Okay, so when we turn on gravity, the Lagrangian have a full standard covariant Lagrangian, and then I can fluctuate the metric by introducing the graviton here. And then I can study the same thing. Go ahead.
Sorry, I had a quick question on the previous slide.
Uh-huh.
Just maybe my intuition is slow to catch up, but sorry, if I send lambda to 0, then doesn't it cost 0 energy to deform this location of this?
Good. This part here is the counter term, which is the energy, right? So this actually goes to infinity, right? So you get a very large thing. But this is a counter term from the work volume theory of the defect. I can remove it. I can just remove it by a counter term. So I can define the operator by just subtracting this piece by hand.
But I'm just thinking, like, so you're saying that it sounds like for some reason, so having this defect wiggle becomes infinitely heavy when it becomes thin?
Yeah. So it wants to be infinitely heavy, but from the point of view of a field theory, this would be like the mass term. I can remove that mass term by hand. It's like the cosmological term from a field theory point of view on the defect.
From the field theory on the defect, if that object is dynamical, it could be there or it could not be there, right? So you
Good. The thing that I want to ask here is whether I could define the operator period, right? I can take this regulated thing and add a counter term, and I would get the genuine topological operator, right? So the question is that, can you always do that, right? So in field theory, I can, because in field theory, I'm allowed to shift the cosmological term if I wish. to define my system. So your worry becomes.
If I were to ask for like the tension of that object.
So let me couple more slides.
Okay.
Let me come back here, and this is what, and I'll explain exactly why you should, when you worry about this tension term. Okay. So let's turn on gravity, right? So when we turn on gravity, you can ask whether, so there are various terms that you get. You will get the bulk term, you'll get the term which is just the expected term in the field theory, but then you get a new term which involves the graviton, which is present, okay? So you get some non-trivial EFT, which will couple the graviton with this Goldstone modes and everything else in your world, okay? So the obstruction that you were thinking about is here. Right? If I look at this coefficient here, right, this is a tadpole term associated to the graviton. So you need the graviton in the bulk to measure the actual tension for this defect from this point of view, right? Otherwise, I could always redefine a new defect where I just shift this thing. But when you have the bulk graviton that is present, right, I have this non-trivial coefficient that's sitting here. And this non-trivial coefficient is the tadpole term where it measures the emission of a graviton from this defect. So now I'm not free to shift this thing around. And then you can ask what happens when you try to take lambda to 0 in this picture. Okay. What happens when I try to take lambda to 0? If I try to take lambda to 0 in this picture, then indeed this thing wants to be infinitely heavy, and I move beyond the validity of the EFT for these things, or it goes to the old argument that if you try to measure something in gravity, if you try to measure charge in gravity in some way, the apparatus itself at some point would have too many degrees of freedom, and then it gravitates and it should make a black hole. So your argument about the tension, your intuition about the tension is correct, but I need the graviton to measure it so that I cannot just send it off to 0 or remove it by something else. And then you get some non-trivial EFT, which is involved in this case.
The kappa tilde and lambda tilde are rescaled by alpha.
So so alpha is just what you usually call is just the parameter. So kappa is a gravitational constant. So the conclusion is that if I want to send lambda to 0, I need to take kappa to 0 first. I have to decouple gravity.
But
then
the question was simpler. What are the tilde in that expression?
The tilde here is just some dimensionless parameter. In order to define this EFT, I have to use dimensionless parameters. Okay. So if I send kappa to 0, then I can take lambda to 0. But if kappa is non-zero, then I cannot take lambda to 0, and then this topological limit is obstructed in the gravitational. Any questions?
I'm still a little bit confused with this cosmological this counter term you're talking about, because I mean my argument was just, I guess, based off the fact that this defect is topological. That it should cost nothing to move it.
Good. No. But my point is that when I define the defect by the soliton, I need to argue that for you, and I have to tell you the condition by which I recover that, right? And the condition which I have to recover that is, one, I need to be able to take lambda to 0 in a way that is consistent. And then I need to do that, I need to show that the goldstones decouple or freeze in a suitable way. And if I have some leftover piece, that I could remove it by a counter term. So those are the conditions that are necessary to obtain the topological defect again. And that's what I was giving you there. Maybe that wasn't clear, right? And the point is that when I turn on gravity, basically this limit of lambda to 0 is obstructed. So the statement is that in field theory, if I want to study this operator, I need to regulate it. If I regulate it in some suitable way, I see that in presence of gravity, that the regulator that takes me to a topological limit is not accessible. Okay? Or more specifically, I mean, you can ask the question: are there other regulators that one could pick? Is unclear. But the thing, at least to me, but for me, the thing that is nice here is that what this choice of a regulator does, it shows me how the goldstone modes are interacting with the bulk, and it shows me that there's they are obstructed from decoupling from your system if I try to take this topological limit. So in the theory of gravity, I should not expect the topological operator to exist. I have 10 more minutes. So there is a broader picture. Okay, you can check this for other examples. In the case, where you have these higher form symmetries, we can play the same games, and then we can find that that in presence of gravity, such an operator there's an obstruction to taking this topological limit, and we expect all of them to be generically dynamic. The goldstone modes exist in general, even when you have finite operators. So this analysis here is just seemed to be apparent for continuous symmetries. Even when you have finite symmetry operators, we still expect there to be some goldstones. And even though there is no current, we still would like to understand what is the dynamics of this goldstone and how do they obstruct, or how do they come alive when you turn on gravity in general. Okay, and similarly, when I talk the discussion, what happened? Oh, weird. Okay. So similarly, if I start to think about these higher categorical things, none of the discussion that I have so far about this goldstone relied on the algebraic properties of these things. So we also expect all of the high categorical ones to come alive in a very particular way. So there is a broader perspective to take here, and I think for sake of time, let me skip it, and then you can ask me about it. So let me go to another. Let me try to conclude. Okay, so to sort of conclude in the last 10 minutes, what this argument is telling is that if I take a topological operator, so we have this whole edifice in quantum field theory where we should think about them, and then I turn on gravity, you have all of these structures here. Our base argument is that you have all of these things will have some goldstone mode, which have to come alive due to the graviton. So you can ask, is this a window to learn something about what could happen in the theory of gravity? Okay. So down here, we typically have some field theory. We expect, as I motivated before, some fusion category that characterizes the properties of all the topological operators. So these will look in some interesting way in this, like this. And then I turn on gravity, right? And the expectation is that at some point, when I turn on gravity, all of these topological operators, they pick up some non-trivial kinetic terms that go up, okay, in a way that I argued before. And then because they pick up non-trivial kinetic term, then they get trivialized as topological operators. They become some dynamical thing, or they could be non-stable and decay to something else, and you recover the statement that there is no topological sector in gravity, or there is no symmetry operators in gravity. So this, to me, is an opportunity that if I give you a quantum field theory, and if I have a good control of these things, do I learn something about some sector of the gravitational theory, in particular, some of these extended operators that exist in the gravitational theory, independent of what we already know is there from the string theory. So, indeed, this lesson we've already seen played out explicitly from a string theory, where we compare two things. One, we compare some low energy supergravity theory, where we can turn off G Newton. Down here, we can actually explicitly construct the topological operators. We can study them. We can study how they and what they do. And in several papers, we classify them. And the observation is that whatever these topological operators that you construct, there's a prescription that we found how to construct them for an arbitrary quantum field theory, is that when you go up in the UV, where there is a string theory, you find that whatever you construct as the topological sector, they descend from the Western terms of some D branes, of some branes, right? So for a string theorist, you know that Western terms is a topological sector of the brain. So you can see this explicitly. You go to the supergravity, you construct some topological operators, you compare them to things in the string theory, you find that those operators are constructed from just restricting to the Western terms of some brains. So what this means that somewhere along the line, the thing that universally turns on is the DBI part of the action. And what is a DBI part? This, of course, is also a DBI part correspond to taking the positions of the brain and then allowing it to fluctuate. Right? The DBI part of the brain is exactly what happens when you study the modes of the brain that allows it to move it around in space-time. And exactly those are the modes that come alive in the analysis that I proposed earlier. So we actually see this play out from a top-down perspective explicitly, and this was a motivation for thinking about this. Okay, so I'll stop here, and thank you for your attention. And then this is another part in this collaboration of these ideas in the collaboration, which might allow us to even learn something about gravity, which is something that I'm excited
Okay, so can you link these ideas to violations of selection rules due to gravity?
I expect to, but we haven't figured out how to compute it. The thing to do is to understand how to reliably get the EFT on the defect on this when you turn on gravity. And then
That's model dependent.
there's going to be model dependent, right? So in the same way that selection rules depend on the system that I'm looking at. So given a system, the selection rules of, okay, or let's step back for a minute. If I give you a quantum system and I have super selection rules, where do they come from? You can think of super selection rules as coming from taking topological defect inserted along some way, and then the insertion of such a topological defect is basically going to fix you in some charge sector. Okay, that's how we understand where super selection rules come from this perspective. So the violation of this selection rule is going to come from saying that if I insert this defect, and now it has some dynamics on it, so that dynamics can leak and connect different selection sectors, right? So from that point of view, if I understand the EFT on the defect, then I should be able to know, to at least hopefully bound the violation of the super selection sectors. That would be the sort of calculation or analysis that one has to do.
So like with just fusion rules, we know that not every set of fusion rules can be a symmetry of a quantum theory, right? Just be like if you just have an operator that squares to 1 plus 2 times itself, there's just no way to implement this. Can these sort of things tell us something about extended objects in string theory? Like does this put some constraint on?
I don't know. I haven't explored this, so I don't have the answer. But if we work the other way background, where I have a string theory and I take a QFT limit, those are well defined and exist. If I take quantum field theory and I have D branes and I decouple their dynamical part and go to some field theory limit, those are topological operators that exist in that sector, right? So what you're saying is that they cannot look like that.
Yeah.
Yeah, so your question then translates to, if I study the dynamics of the brain, is there some constraint that I could have learned, deduced, and so far? So I don't know the answer of that completely, right? Because part of this story is actually now, it leads to a new question, which is that, we think of D brains as being classified by some K theory in string theory. And then the question that you have to ask, does this classification scheme map to some classification scheme of fusion categories?
Yeah.
And how to make this precise? And there's a lot of work now where people are trying to understand this, right? Trying to understand how the physics, what we know and how we talk about D brains maps to what we know and how we talk about categorical theory, following some of our papers that we wrote. Yeah. So hopefully we'll have a better answer to that. Yeah.
Yeah. So I like the bottom-up perspective you were offering, but I was curious. So I guess we don't expect that you can couple any QFT to gravity and it will be fine in the UV. So do you expect that this, like, you'll be able to see that somehow in this construction, or do you think not? It won't show up.
So your question is that if I have a quantum field theory and I couple it to gravity, there could be some swampland argument that tells me that this is bad. So this thing here that is not necessarily going into that direction, right? It could be that, you know, what happens is you take a quantum field theory, it has some fusion category associated with it, and then you say that, okay, this fusion category maybe come from some non-trivial sector of the quantum gravity. Is that sector allowed or not allowed? Right? But that would be a way to answer your question. But I think we're like very far from such a thing, you know, already making the statement that somehow the fusion category should lift some non-trivial structure of extended operators. We're just starting to sort of figure out what that means and how it gives me the gravity. But maybe, you know, related to his question here, that that extended operators cannot behave in some arbitrary way, and then then maybe I can rule out some versus the other.
So maybe a variant of the Gabriel's question. Again, is this related to, for instance, the cobordist conjecture in string theorems?
So the cobordism. Okay, so cobordism now is becoming one of those words that's used and misused in various ways. So to be clear, the cobordism that you're talking about in string theory is the fact that we don't expect any interesting topological structure in a theory of gravity. So if I have a string theory and it with some boundary and have some non-trivial bordism group, then that bordism group has to be trivialized in the bulk. That's what you're saying. And the way it gets trivialized is we say that there must be some charged object inside that sort of trivializes that thing. So that argument is an argument that tells you about interesting classes of brains that we cannot see via standard techniques. You know, that tells you that you have to have those charged objects that have to live there in some very interesting way. That's what those things tell you. So then the way that I would interpret your question is that, you know, if I have brainy things that I get from some argument by trivializing some bordism group, could I have seen something like that from the field theory, specifically the bordism structure itself, and so on? I don't know. But that could be an interesting thing to try to explore.
Yeah, I was wondering if you had any, like, you had mentioned earlier that doing continuous fusion category, whatever that would mean, is hard, or the unitarity is hard there. I wonder if you could expand on that a little bit, or if there's any intuition about why it's hard.
I cannot give a good physics intuition personally why it's hard. I mean, I can wave my hands, but I don't want to.
I'll take a wave. Okay, that's fine.
Okay, maybe we'll thank you both
Yeah.
and